All right, folks, what we want to do now is we want to review oxidation numbers, and then we'll go over reducing agents and oxidizing agents, and we'll end with an example. So just to review, let's go ahead and look at this. So whenever we're assigning oxidation numbers, we're looking at the charge on the atom, what it would possess if the compound was actually ionic. So we're looking at covalent species, and we're saying, okay, what would happen if this was ionic? What would the charge be on the individual components of our molecule or our species? And then we'll also be able to do this for ionic compounds, just like we would earlier in this class. So as we look at oxidation numbers of elemental substances, I've listed iron and hydrogen. So iron exists as a solid, as a monatomic, and then hydrogen exists as a homonuclear diatomic. So both of these are in their elemental phase. So they have a oxidation number of 0. If you have a monatomic ion, so that just means one ion all by itself with a charge on it, whatever its charge is, that is the oxidation number. So for instance, magnesium 2 plus has an oxidation number of +2, and the fluoride ion F minus has an oxidation number of -1. So then after here, what you're going to do is you're looking at compounds, you'll have a hierarchy. So you'll assign oxidation numbers to alkali and alkaline earth metals first, and then we'll start to look at some more of those atoms in the P block. So alkali earth metals, anything that's in the first group, that first column, so for instance like sodium and lithium, we would assign those a +1 oxidation number. So for sodium chloride, sodium would have a +1, and that would mean that chloride would end up having a -1. And lithium hydroxide, lithium would be +1. Then we'll figure out how to deal with the OH in just a second. For alkaline earth metals, that's things that are in group 2. These have a +2 oxidation number, assuming they aren't in their elemental phase, that they're in a compound. So for instance, magnesium chloride, magnesium would have a +2 oxidation number, and calcium hydroxide would have a +2 oxidation number. So now these are when the rules really become important, because we start to deal with hydrogen and oxygen and halogens, and we have to figure out what order do we actually assign the oxidation numbers in. So with hydrogen, most of the time, nearly all the time, hydrogen will be combining with nonmetals, and what we'll see is if it's combining with nonmetals, it has an oxidation number of +1. So for instance, in H2O, hydrogen has an oxidation number of +1, and in CH4, hydrogen has an oxidation number of +1. But as soon as it starts behaving as the anion with a metal, so for instance, sodium hydride, well, we know that sodium would have a +1 charge on it, or a +1 oxidation number, so the hydrogen has to have that -1 oxidation number. So if hydrogen is with a metal, it will have a -1 oxidation number. You do have to be careful, because if hydrogen is with oxygen and then with a metal, so for instance lithium hydroxide up here, hydrogen would still be +1 because it's with another non-metal. From here, after you've assigned hydrogen, the next thing you can assign is oxygen. Oxygen is almost always -2. Every now and then you may have to calculate for something like hydrogen peroxide, and it would have an oxidation number of -1 for oxygen, and I'll let you prove that to yourself. So oxygen would have a -2 oxidation number, and then halogens have a -1 oxidation number as long as they are not behaving as the cation. So what I mean by that is, if we were to consider species like ClF5, well, overall this molecule is neutral, so we can't say that chlorine has a -1 oxidation number, then there's 4 fluorines that have a -1 oxidation number, because if we took the sum of those, that would be -6, and -6 does not equal 0. So what you'd have to do is you would assign it to the anion, which is the last thing that's listed here. So we have the fluoride part here with a -1. So we are trying to figure out what the oxidation number is for this chlorine. So chlorine is our unknown. So we'll have X plus, then we have 5 fluorines, each at a -1 oxidation number, equals 0. So that means in this particular case, chlorine has a +5 oxidation number. So if you have a molecule where a halogen is your central atom, make sure you're going through and double checking what its oxidation number is. It's not just going to be -1. So before we get to our example, let's go ahead and make sure that we do understand what oxidation and reduction is. So oxidation is whenever you are increasing the oxidation number, and that means that you are becoming more positive. Okay, so you are going to be losing electrons. Remember, oil rig, oxidation is loss of electrons, whereas reduction is a decrease in the oxidation number, so reduction is gaining electrons, so you're going to become more negative. It doesn't mean that you actually have to have a negative oxidation number, it just means that it's becoming more negative. And then kind of the tricky part, if you're talking about the reducing agent, that's actually what's being oxidized, and the oxidizing agent is actually what's being reduced. So let's go ahead and try one last example together. So here we have 2Fe plus 3V2O3 yields Fe2O3 plus 6VO. So the first thing we want to do is we want to go through and assign oxidation numbers to everything, and then we can go through and figure out what's the oxidizing agent, what's the reducing agent. So let's start with iron because it's all by itself. So since it's all by itself and there's no charge, we know its oxidation number would be 0. All right, now let's look at our second compound. We have V2O3. So we know that oxygen has an oxidation number of -2. So we have to figure out what the oxidation number is for vanadium right here. One of the things you want to make sure you're doing whenever you're assigning oxidation numbers is that you actually don't need to pay attention to what the coefficients are. You're just going to look at the subscripts, so what actually makes up the molecule. So for this one, we have V2O3. So if we're trying to figure out the oxidation number of vanadium, we know we have 2 vanadiums, so we'll call that 2X, plus we have 3 oxygens, each with a -2 oxidation number, and overall this is a neutral molecule. So we can go ahead and simplify this. So we have 2x minus 6 equals 0. So 2x is equal to 6. So x is equal to +3. So vanadium has an oxidation number of +3. We can go through and complete something similar. For Fe2O3, we'd see that oxygen has the oxidation number of -2. And in a similar way to what we just did, we're more or less going to copy this math, but we see that iron ends up having a +3 oxidation number. And then for VO, so here, oxygen has a -2 oxidation number. And since overall the charge is neutral, that means vanadium has to have an oxidation number of +2. So let's go ahead and figure out where our electrons have been moving around. So iron, so we have iron, we have oxygen, and we have vanadium. So iron started out with an oxidation number of 0, and it went on to have an oxidation number of +3. So iron was becoming more positive. So it was losing electrons. So it was being oxidized. Oxygen in the reactant started with -2, and then in both places that oxygen is found in the products, it still has an oxidation number of -2. So there is no transfer of electrons here. And then finally for vanadium, vanadium started out with a +3 oxidation number, and it ended with a +2 oxidation number. So even though both of these are positive values, it's still decreasing. It's becoming more negative, so it was reduced. So that means the oxidizing agent is what's being reduced, so we would say that V2O3 was our oxidizing agent, and then our reducing agent, which is what's being oxidized, is the iron.